Okay, let us proceed from where we left last time, and we will basically look at event driven schedulers. Cyclic schedulers we had seen to some extent, and some parts we could not really finish in the last lecture. We will just quickly review those, and then we will look at event driven scheduling, which is the main focus of this hour. So, the cyclic schedulers we had seen that they are driven by clocks, and the frame size, the scheduler wakes up at every frame boundary and looks at what to do. And then we are trying to work out examples, trying to find out what can be a suitable frame size which can, on which the tasks can run satisfactorily, right. And we had said that frame size is a important constraint, and one thing possibly we did not very convincingly tell you last time was about the minimum separation of the frame boundary and the task arrival, right, which is equal to GCD f comma pi. And I said that, see, one of your predecessors he actually gave the simplest proof. So, let me just redo that proof now, because it was not really very convincing argument that I did not portray the argument that he had given. So, just look at it. What he had said is that so we are trying to work out the proof which was given by one of your predecessors on a bonus problem, like I gave you today about the bonus problem to find out the frame size, not frame size, I think the schedule that needs to be stored when the frame size does not divide the major cycle. Similarly, on a similar assignment somebody had given this proof. So, said that, see, assume that for some occurrence of the task and the frame occurrence, the separation between the frame size and the task arrival is less than GCD. Assume, so let me just write that much. Assume that the minimum separation is less than GCD, for some let us say kth occurrence of the task, and let us say mth occurrence of frame. So, we have a situation where m frames have occurred and the task has repeated k times, and then we have a situation where the task is starting, the difference between the frame start and the task's arrival is less than GCD. So, in that case we will have k into f and m into pi minus k into f is less than equal to GCD. Right, and this has to be greater than 0, because if it is 0 then they are actually coinciding. I mean, it is the earlier frame. If it is less than 0, then it is in the earlier frame, right. So, GCD squarely divides pi and f, that is the basic definition of GCD. So, you divide GCD on all sides. So, from here we can get 0 is less than equal to some I1 into Pi minus I2 into F is less than equal to 1, right. So, we have for all these are integers Pi, I, I1, I2, F. So, two integers which makes the value lie between 0 and 1 is not possible, right. So, it is a contradiction. So, this cannot occur. So, that was the proof we had given, very nice proof, it is there in the book, the proof that was given by him.
Cannot be less than, but it can be greater than only.
No, we are saying that GCD F comma Pi gives the minimum separation between the frame boundary and the task's arrival. It cannot be less than GCD.
Yes, sir. It cannot be less than,
It can be more.
greater.
So, the worst case,
Equal to GCD.
see the worst case of a task scheduling occurs when the task arrives too near the frame. See, let us look at this situation. See, let us say these are the frames.
Sir, but I am talking about the proof, sir. The proof is just saying that the minimum separation cannot be less than GCD.
Yes.
It is not saying it is equal to GCD.
Okay, does not matter. So, if we can make it run for GCD, if we can schedule it, then
the proof just says that it may be greater than or equal to GCD.
yes, that is what we are saying. GCD is the minimum. GCD is the minimum, right? Separation between two tasks. So, if we can take care of that, see the worst case scheduling condition occurs when it is less than GCD. More than GCD is not a problem. Just look at here. See, if we have a task arriving here, then let us say the deadline is here, then we can run it on this frame, right. Now, if the task arrives here very close here, right, and then possibly that we do not even have one frame. So, the worst case for any task scheduling occurs when it is too near to a frame boundary. So, then the available frames are much less. I mean, there may not be even one frame if it occurs too near a frame boundary. So, for large GCD, sorry, any occurrence separation larger than GCD, we do not have a problem. If it is lower than GCD, then we might have a problem. Yes.
So in the proof, if you could just
yes, yes. Yeah.
We are assuming that it is a kth occurrence of a task.
Yes.
Mth occurrence of a frame.
Yes.
So sir, in that equation that we have written,
Yes.
wouldn't it be k into pi?
Yes.
And m
Okay.
into
Okay. Yeah. That's. I mean, I was just trying to give you the line of argument rather than the one. Actually, what he says is that since I have written kth occurrence of a task, we should have k here, and we should have m here. It does not really matter, because k will also k into pi will divide GCD, and m into f will also divide GCD. So, this was the proof. Many came with different proofs actually, and this was the proof which was the simplest, and that we have documented in the book with acknowledgement to him. So, let us proceed what we are saying. Now, the cyclic schedulers have one disadvantage. The disadvantage is that since we have to try out various frame sizes and try splitting the tasks and so on, many times you will find that we are not able to select a suitable frame size, or maybe we are selecting a frame size which does not lead to a good schedule. CPU times may be wasted in many frames, right. And therefore, for many situations we may not even find a schedule, even though it is possible to run them using a cyclic scheduler, we can't run them. I mean, at least we are not able to find a proper schedule, and breaking tasks into many parts will make it still higher overhead, context switches and so on. Now, before we look at the event driven scheduler, just a few minutes, as we were saying earlier, that what we looked at till now, the pure cyclic scheduler, which just handles periodic tasks, but there will be situations where it also might be required to handle at least few aperiodic and sporadic tasks. So, how can this be handled? We need to use the unused frames and also the slack time that is left out after a task completes. So, agent when a sporadic or aperiodic task arises, the scheduler somehow need to use the slack times and the unused frames. So, this is the scheduler algorithm modified. See, earlier it was just looking at the schedule table and then each frame size it was trying to run the next task. Now, it is doing the same thing actually, trying to find out the next task to run. Say k is equal to k plus 1, setting it to find the next task, right, and if it finds the end of the table, it just starts from the first task and then it runs the current task, and if it completes even before the interrupt comes, it runs the sporadic tasks, and even if there is still more time, it runs the aperiodic tasks, otherwise it just idles, right. So, if there is no task to run in some frame, it finds that nothing is to be run in some frame k, then it will run the current task and so on, and similar is the case when the task completes early, right, until the clock interrupt comes. The periodic timer interrupt comes, it will keep on doing this. Now, let us look at the event driven schedulers. Here, unlike the clock driven schedulers, this can handle both sporadic and aperiodic tasks very easily and definitely used in more complex applications. These are necessary to be used. The cyclic schedulers have their limitations, only very simple systems they can handle. For example, we are just discussing about a cell phone, right, many tasks, many are aperiodic, you are sending a message, receiving, making a call, etc. These are sporadic tasks, and a cyclic scheduler can't handle this. In an event driven scheduler, the scheduling points are defined by task completion and arrival events. So, whenever either a task completes, the scheduler will wake up and it will look at what to run next, and so is the case when a new task arrives, it will be woken up and it will try to see if the new task is a very high priority, then it can run and preempt the running task. So, these are the event driven schedulers are preemptive schedulers, because if a higher priority task comes, the current task may be preempted. So, just see here we are not talking of clock at all, but implicitly a task arrival might be on a clock cycle. The simplest event driven scheduling that we can think of is a foreground background scheduler. We will just discuss about the foreground background scheduler shortly, just a minute or so, because that is the simplest and not really used in applications, just for a concept. So, the scheduling points are a task becoming ready and a task completing its execution. Okay. Before the foreground background, let us look at something which we had already discussed in a first level operating system course, is a time sliced round robin scheduler. This is also an event driven scheduler, but it also has a concept of a time cycle, I mean a time slice. So, this scheduler is actually discussed in the operating system books. We will not spend time on this, excepting just making a passing remark saying that see here there are two types of events that are considered. One is a task completing or suspending itself, and also the clock interrupts, because after a time slice is over, it needs to suspend the task and start the next task, right. And we will see that these are not suited to real time task scheduling, not used. We will have quite a bit of discussion on Unix later on and the Windows. We will see that the operating system they have, they can't really run real time tasks. We will identify the reasons. The event driven schedulers, they will preempt the currently running tasks if a higher priority task arrives, and these are also called as greedy schedulers, because as long as there is a task to run, it will run them. Unlike, let us say, cyclic scheduler, we had some part of a frame idle even though there is a task which could have run, right. So, here as soon as a task is there, it will be run. So, that is why these are also called as greedy scheduler in the literature. As we were mentioning earlier, lot of research was done on event driven scheduling on uniprocessor in the 1970s. Thousands of papers were published, but if you know two of these algorithms, the EDF and RMA, then you know all other algorithms, because these are the optimal ones. Let us look at this, we will see why these are optimal. Okay, before that, let us look at the foreground background scheduler, which is the simplest event driven scheduler. Here the real time tasks are run as foreground tasks, and non real time tasks or sporadic and aperiodic tasks, these are run as background tasks. And among the foreground tasks are the real time tasks. At every scheduling point is basically either arrival of a real time task or completion of a real time task, right. Those are the scheduling points. The highest priority foreground task is scheduled, and a background task runs when no foreground task is ready. So, if TB is the background task and its processing task is EB, then the time for the background task to complete we can find out by finding the unused processor time by the foreground tasks. Let us say the foreground tasks are the periodic tasks. EI by PI is the utilization they have on every PI, right. EI by PI is the utilization of the processor for the task TI. So, for every task, if we consider, sigma EI by PI is the total utilization, is not it. So, every 1 millisecond or 1 unit of time, sigma EI by PI is utilized by the higher the foreground tasks, and 1 minus sigma EI by PI is the time that is available for the background task to run. And therefore, the background task will take CTB time, which is EB by 1 minus sigma EI by PI. Does that appear okay? Simple result, is not it? Is it okay? Yes, anybody has difficulty with this? Just a example. So, if there is one foreground task, periodic one, 50 millisecond, I am sorry, this should have been E1. E1 is 50 millisecond, P1 is 100 millisecond, D1 is 100 millisecond. So, the foreground tasks consumes 50 millisecond every 100 millisecond, and there is a background task which takes 1020 millisecond. So, how much time will the background task need to complete? Can somebody do it? See, the problem here is actually okay, this has to be corrected E1 is 50 and P1 is 100 and the background task takes 1020 millisecond. So, once the background task arrives, how much time will it require to complete? 2040. So, how did you get that?
20 by 1 minus 50 by 100.
Okay, let us see the answer. Okay, we do not have the answer there worked out. So, let us see. See, every 100 millisecond it gets 50 millisecond, right. So, it will get 1000 millisecond into 100, right, in 2000 milliseconds, right, and then it will need another 20 to run, another 20 to complete. So, 2020. Why 40? See, once it gets a frame to run, it will run. I mean, once it starts running, it will take 20. So, why 2040?
Sir, if you substitute the values for EI and PI in that.
No, do not use the formula blindly. Just assume, see, it runs, the task runs up to some time, right? It keeps on getting time, and next time it just gets time, it will complete it. So, that is the same question as in high school they used to ask the monkey climbing a pole, which is, do you remember that? The problem is something like this: a monkey climbs a pole, and each time the pole is oily, like class 2, 3 or 4. So, each time it jumps some 5 meters and it falls down 3 meters, right, and the pole height is, let us say, 54 meters. So, the final time it jumps, it does not fall down, right, something similar to that. So, here also the last time it runs, so each time it just keeps on getting 50, but the last time it gets it, it will run it. So, 20 only it will take, is not it? Does that appear okay? Okay. So, let us just make that problem slightly more complicated. Assume that there is a context switch time of 1 millisecond required whenever there is a switch from one task to another. So, what will be the completion time of TB now? Simple extension of the previous answer. Yes, anybody would like to answer this question? When we need to consider the context switch overhead of 1 millisecond every time a new task starts. We had said earlier, recaptured the first level operating system course, when a task starts, a context switch time is involved. 2060. Anybody has any different answer? Anyone wants to add anything? 2041. Okay, see, it is not very complicated. See here that each time a task starts, we need a context switch time and it runs for 50. So, this is the 51, right, and then the background task starts and runs up to 100, right, then the new task comes here. So, the background task effectively gets 2, 1 is taken out here, 1 is taken out here, 2, right. So, it is getting every 100 millisecond it is getting 48, instead of 50 it is getting 48. So, 2000 by 48, 20, what was that, 1020, is not it, 10. So, if we find a multiple of 48, it will be 480, 960 and then 1920 and 48. So, 21, so that becomes 2050, is not it. So, 1968 and we have another 32 plus 20. So, another 52 to run, right. No, it should have been 2100, is not it. 2100 would have made it plus 48, 6, 10, 1, 2016. So, another 4 it needs to run, and when it runs 4 it will also incur a. So, the situation is that it has run up to here, and then another 4 has not run. The last one is 50, sorry, this is 52 times, is not it. No, not 52, 22 times, and then 21, is not it. 2100 times 100 into 21, 2100, and then another 4 is remaining, right. So, 50 will run here, the task, real time task will run 50, foreground will run 50, and this will run another 4 here. So, this is 1 taken out, 1 taken out here. So, 2, so 52 plus 4, 56. So, 2156. Is it okay? So, each time it is keeping on getting 48 out of 100. So, we will find out when, and last frame we need to be careful little bit, because the foreground task will come and start running here, and it will involve a context switch, and then the remaining part 4 or something was remaining, that will run, but again a context switch will be involved. The last one you need to be bit careful. Is that okay? Simple problem. Okay. So, so far we did not really discuss about the schedulers that are actually used, the event driven schedulers. So, we will see that we will first look at the static priority scheduler. We call it static priority schedulers because the priority will be assigned by the programmer before the system starts, and during the runtime the priorities do not change. Whatever was assigned by the programmer during the design time, that will continue to hold, and here this rate monotonic algorithm is the optimal static priority algorithm, extensively used. So, very important one. Throughout we will fall back on this basic concept of a static priority computed by the programmer does not get changed. And then the other is the dynamic priority algorithm, which is the earliest deadline first. So, here the priorities can change during runtime as the task, the system runs, some task becomes more higher priority, and another one which was earlier higher priority, its priority might reduce depending on what is the deadline. So, based on the relative urgency of completion of tasks, the priorities keep on changing as the system runs, and many algorithms exist which are dynamic priority schedulers, but if we know EDF, we know the best algorithm that is possible. It is the optimal uniprocessor scheduling algorithm, and earlier we had said optimal is one if it can run some tasks then the other dynamic priority schedulers, they may or may not run it. But if another dynamic priority scheduler is able to run some task, then definitely EDF will be able to run it. So, let us look at the simplest scenario when we have independent tasks. A task does not need result from another one, no resource sharing between tasks, and no precedence ordering. That is, one task does not need to wait for another task to complete. This is not really a practical situation, that we have tasks which are independent, not needing results from each other, no constraints among them. But to understand the scheduler, we need to start with this, and as we proceed we will make it more complex. The resource sharing etc. exists. So, this is the optimal algorithm. If it cannot schedule some tasks, then it is no use trying out other tasks, other schedulers. If something is not schedulable by EDF because it is the optimal algorithm, then other algorithms we cannot run this. Handles both periodic and aperiodic tasks, and given a set of task, the check for schedulability here is that sigma ei by pi is less than 1. So, the utilization of the processor due to all tasks, as long as it is less than 1, very natural, because no, if the number of the time required to run is more than 1, we can't run on any processor, isn't it? Utilization 1. So, the constraint is actually nothing other than the common sense how much a processor can run. So, it basically we can say that if a task set can at all be run, then EDF will be able to run it. So, this is both the necessary and sufficient condition for schedulability. Okay, I think we can say that it is a sufficient condition for schedule. I think necessary is not there. If it is this is satisfied, then definitely it will be able to run, but it is not necessary that. What do you think? Is it necessary?
Second condition is necessary.
Okay.
Second condition.
Okay, this one. Yeah, it is okay. Then it is all right. It is both necessary and sufficient. Okay, it is a necessary condition and also a sufficient condition. Okay, fine. So, let us just look at an example whether EDF can run this. So, there are 3 tasks, periodic tasks, and the period and deadline are the same for each of them. One is period 4, another 5, another 20, and the time is run time required, execution time required is 1, 1 and 5. So, we just need to check the utilization for each of these tasks. So, this is 1 by 4 is 0.25, the first one, second one is 0.2, isn't it, and the third one is how much? 0.25. So, 0.25 plus 0.25 plus 0.2, 0.7. So, less than 1, and this is schedulable in EDF. We said that EDF is a dynamic priority algorithm, and if it were a dynamic priority algorithm, we should be able to tell how the priority values, what is the priority value of a task at any instant, and also how this change with time, and say that see at this point see it was 10 and then it has become 5 and so on, then we can call it as a dynamic priority algorithm. But what about EDF? We just saw that the algorithm is simple, that any task which has the shortest deadline, earliest deadline will be executed, right. So, where is the concept of a dynamic priority here? Anybody would like to answer this question?
As the deadline of the as the deadline comes nearer to the task,
Yes.
then its priority should be increased. Earliest deadline.
No, but what is that priority failure?
When a new task arrives,
Yes.
if its deadline is
more
earlier,
nearer to the previous task, then we need to set its priority to a more higher priority. We have to set it.
So at every scheduling point, we
Yes.
find out how much of the execution time is left. Like,
Okay. Okay. And then what is the priority? How will the priority be computed here?
Sir, whichever task is supposed to finish the first,
Yes.
that will be given the highest priority. From at every scheduling point,
Okay.
suppose or
okay,
whenever
so
the
that-
task has arrived.
Okay.
and
So
then we
a
have to
task.
see which task
Okay.
is
So what basically he says that a task arrives, it keeps on waiting until its deadline is very near, and as it keeps on waiting, its priority increases. We can think of it, right? Another task which was running, and next time it came, possibly its deadline was quite far, and then the task which was earlier waiting is running, because now that task has become a higher priority, isn't it? Yes. So the longer a task waits in a ready queue, the higher is the chance of it being taken up for scheduling according to the EDF. So even though we can't really assign a concrete value saying that its priority is 20 or 30 or something, but we can imagine a virtual value which keeps on increasing with time until it is scheduled, right? And the next time it comes, it has a lower priority, and as its deadline approaches, or if its deadline is already high, is low, is less, deadline is very less, then its priority will be increased, right? Very simple algorithm. Just examine the deadline of every task, find out the one which has the lowest deadline, and then run it. And it is also the optimal one. We are not going to prove why it is optimal. The proof is slightly involved actually, we will not prove it, but it is the optimal one, but it is rarely used. As we will see, the commercial operating systems and the systems which use any operating system at all, see that EDF is more of a concept rather than being actually used. None of the commercial operating systems actually support EDF scheduling directly. So there must be some major disadvantages, even though it has so nice properties here, very simple, efficient, also optimal. There must be some disadvantages, otherwise it could have been used heavily. Let us see the disadvantages of EDF. Many disadvantages, but three main disadvantages. The first disadvantage is called as transient overload handling. Second is the runtime inefficiency. The third is resource sharing of tasks creates severe complications. Let us look at each of these points. The first shortcoming is the transient overload handling problem. EDF, see, transient overload, we had said earlier that sometime the events just occur together. For example, there is a fire situation and then the fire alarm was sensed and it just set up a avalanche, lot of events occurred immediately after that, right? It rang a bell and then the water, this thing sprinkler was switched on and so on. Many events could happen at the same time. So these are the situations where suddenly many tasks need to run, and that is called as the transient overload. So when a transient overload occurs, then EDF can miss a deadline, right? And if it misses a deadline, that is not too bad actually, but the main problem here is that the highest priority task might miss its deadline. It does not guarantee anything. A low criticality, low priority task might run to completion, whereas a high priority task might miss deadline. Another situation, let us consider this, that for some reason a low priority task is getting delayed, maybe it has gone into a loop or something. So, in that situation also a higher priority task can miss deadline. So, whenever there is a transient overload, it is very difficult to predict which task will miss its deadline. The second problem is that EDF is not very efficient. Just let us consider an implementation of EDF. Here you see a simple implementation may be we keep all the tasks sorted according to their deadline, right, and then we select the shortest deadline. So, each time an event occurs, that is task completion or arrival, we just adjust the queue of the tasks and we just select the one at the front of this queue. You can use a priority queue. On which we maintain the tasks based on their deadline, right. The shortest deadline has the highest priority or at the top of the queue. So, what is the complexity of maintaining a priority queue? Yes, you have done, how is a priority queue implemented? Let us say you are doing a C program or something, how will you implement a priority queue? Yes, anybody knows how to implement a priority queue efficiently? The most efficient way priority queue can be implemented. Let us say you are writing a C program or something.
You can use a heap.
Okay. A heap is the most efficient implementation of a priority queue, and log n to the base 2, where n is the number of tasks, is the complexity of maintaining a priority queue. If you brush up your knowledge on the basic data structures and algorithms, you will see that priority queue is implemented using a heap, and that is the most efficient implementation of a priority queue. And log n is the complexity of maintaining a priority queue, and each time an event occurs, we need to adjust the priority queue, right. So, it is not very efficient, because that overhead will be incurred in every event occurrence. The third problem is the most severe one actually, is the resource sharing among tasks. We had said that it will be very unlikely that you will have a system where the tasks do not share resources. All practical situations, we will see that the tasks share resources. As we discuss further, we will see that. And here in this EDF, it becomes very difficult to allow tasks to share resources. For example, the critical sections. If we use EDF and then we have this resource sharing requirement, then we will see that the tasks will miss their deadline. We will have that discussion little later, that how resources be shared, because so far we have been discussing that tasks are independent, do not share resources and so on. We are soon going to discuss about how resources can be shared. We will generalize our discussion now, that independent tasks not sharing resources, etc. We will generalize that, and then we will see that EDF would make it extremely difficult for tasks to share resources. Okay, so let us proceed. We had seen the situation where the execution time and the period, the period and the deadline were the same, but we can have sometimes a situation where the task period is different from its deadline, and then we need to generalize our earlier expression, that is sigma ei by pi less than 1, we have to make it sigma ei by minimum of pi by di. So, if the deadline is less than pi, then we will have to choose the deadline value here, right. But if Pi is equal to Di, it does not really matter. So, this is the new expression when
what will happen if Pi is greater than?
Okay.
Sorry,
Pi is less than Di. Yeah. So, that when Pi is less than Di, then this becomes a sufficient condition. That means, if this is satisfied, then definitely it will be schedulable, but not a necessary condition. Even if it is not satisfied, we will see that it can be schedulable. So,
it is occurring before the previous instance has completed.
No, it has deadline is occurred after the next instance has occurred. Di is greater than Pi.
Greater than Pi.
So, the deadline is even after the next occurrence has occurred, right. So, in that case, this is a sufficient condition. If this holds, okay, definitely they are schedulable, but if it does not hold, we can't say that they are not schedulable, we will have to check out. Okay, so this we had seen that not a very efficient implementation will be just to maintain a queue, fast in fast out queue, but here each time selecting the smallest task, the task with the smallest deadline, you will have to scan the queue once, that is n, is not it? Each time you have to look at every task n. This can do it in log n, right. You need to maintain the queue. Here you do not maintain the queue, you just have to look up time takes more. But still a more efficient implementation of EDF can be possible, where you fix the maximum number of distinct deadlines, whether it is 5 or 7 distinct deadlines you can give, let us say 0 to 10 and then 10 to 20 and so on. And then a queue is maintained for each distinct deadline, and the top of the queue has the highest, the deadline for that band, lowest deadline. So, when a task arrives, its absolute deadline is computed and inserted into queue. So, you just have distinct set of deadlines, and each time you just need to manipulate only the first few tasks, right, check at their deadline. So, to run it you just need to take this one, the highest one, the top here, and then you need to look at the top one here and just put them in the appropriate levels, right. So, this will be a much more efficient implementation, and of course, each of them will be a priority queue. So, we will stop here. If you have any questions, we can just discuss about that, otherwise we will stop here. So, any questions so far? We looked at the dynamic priority scheduler, right, that is the EDF, and we said that EDF is the optimal algorithm, and but it is not really used very much practically, and then we identified the reasons, right. So, what were the reasons? Anybody remembers?
Transient overload.
Yes, it does not, if there is a transient overload, then EDF will have problem. Yes, it is inefficient, implementation is inefficient. If the number of tasks is large, then the time the scheduler will take to look through the task and select the one that is need to run is high, and also to arrange the queues each time. And any other different? Yeah. So, we had said that resource sharing is occurs in every practical situation, and in EDF, if we try to extend it, see, so far we have been looking at independent tasks, but when we try to extend this to handle situations where resource is shared, we will see that it will become extremely inefficient, and tasks can miss their deadline. So, we will stop today, and in the next class we will discuss about the static priority algorithm, that is the rate monotonic algorithm, the optimal algorithm, heavily used, simple algorithm again, and we will spend more time on that. See, EDF we really did not spend more time, because after all it is more for our reference, and it is the optimal scheduler. If EDF cannot schedule, nothing else can schedule. But RMA is the one which is used extensively. Every commercial operating system has a means to support at least RMA, right, if nothing else, or variations of RMA. So, we will see the RMA and how resource sharing is done, how task precedence can be handled, and so on. We will spend at least 4-5 hours discussing RMA. So, we will stop here. Thank you.